All right. Good morning, everyone. Hi, I'm Marius.
And I'm Dion.
And let's dive right into our talk, Overcoming State, Finding Baseband Vulnerabilities by Fuzzing Layer-2. Let's look into what the next 35-40 minutes will be about. We will be talking about basebands on smartphones, about emulating them and fuzz testing them. And in contrast to prior work, we will focus on fuzz testing layer 2 of the cellular stack.
We will also talk a bit about the challenges that we had to face, for example, actually constructing the fuzzing tasks, dealing with the fuzzing roadblocks, and also how we actually confirm the results from our fuzzing experiments over the air.
And after overcoming these challenges, we actually see something like this. Connection bars going to a connection disappearing. We triggered crashes over the air on real phones. And one very interesting fact about this is although we fuzz tested or aimed our fuzzing at layer 2, all the crashes we found were located in layer 3. But now, let's take a step back and talk a little bit about basebands in smartphones itself.
So basebands typically consist of a collection of processors. The main two processors are the application processor, or the AP, and the cellular processor, or the CP. The AP is mostly responsible for running things as Android, and the CP is responsible for dealing with all radio connectivity. Throughout this talk, we will refer to the CP as the baseband. And the baseband itself consists of millions and millions and millions of lines of highly proprietary code. It also implements most of the layers of the communication stack, and it contains lots and lots of legacy code, interesting parsers, interesting functions in general, really obscure features. But more importantly, the baseband is also can be reached with over-the-air packets and also internet packets, making it a really interesting attack surface to look at.
So how do cellular basebands on CP implement all of these different functionalities? These cellular processors run custom firmware. Most of the time they deploy a real-time operating system, or RTOS in short, and the RTOS is responsible for two main functionalities. First of all, it provides the core operating system functionalities. So everything which you would expect from an OS. It provides a scheduler, timers, interrupts, and so on. It also provides the notion of tasks, which are basically what we would call on desktop operating systems processors. And these tasks can interact with each other via messaging mechanisms provided by the RTOS. Then the firmware running on the CP implements large chunks of the cellular stack. For doing so, what we see is that the cellular stack is split into these different tasks, and these tasks communicate with each other using the message queues provided by the operating systems. So messages which come in over the air to a cellular baseband will be dispatched by the different tasks and passed across the different stack by traversing the message via the tasks.
So recently, we've seen a very awesome shift in doing baseband research. So on the slides, we've only shown a few examples of baseband research, only from this year and the year before. So as you can see, there are quite a lot. For example, the over-the-air under the radar talk, Black Hat talk from last year, and the cracking the 5G Fortress talk from yesterday at Black Hat.
And what about our research? So when we started looking in the research we're presenting today, we were looking at the state of the art. And we were basically noticing that most of the works out there, especially in terms of finding memory vulnerabilities and memory corruptions, were focusing on cellular layer 3 or higher. We will come to what are the different layers in the next slide, so please bear with me for a second. Also, if we just look at the talks and works from last year and this year, 2023, 2024, we only see two works which actually were involving some sort of layer 2 vulnerabilities. 5Ghoul did some over-the-air fuzzing, which also yield to the discovery of bugs in layer 2. And the work, There Will Be Bugs Exploiting Baseband in Radio Layer 2 by the people from Task, did involve actual exploitation of layer 2 bugs. But when we started our work, this were not available. So we were thinking, hey, let's have a look at layer 2 ourselves in cellular basebands. And we went the approach of going for the lowest hanging fruit. So we decided to select, let's look at GSM layer 2. So GSM is 2G, and from an attacker perspective, this gives quite some interesting capabilities. Because in contrast to more recent cellular generations like 4G or 5G, there's no mutual authentication between the phone and the base station. So attackers can easily spin up a rogue base station and make the phone connect to it. Also, we decided let's go for fuzz testing or fuzzing, because fuzzing has just been proven very efficient in finding those type of bugs we were interested in to look at. Now, I already said it, we want to look a little bit at the GSM or 2G protocol stack to understand more where our work is actually based. So like any network stack, the lowest layer, layer 1, actually deals with the physical layer. No big surprises here. The maybe only difference to other network stack is that here the physical layer is obviously over the air, as we're dealing with radio communication. So the file layer gets incoming packets and passes them on up to the data link layer, the layer 2. In the GSM cellular stack, this layer is the so-called LabDM, or link access protocol on the DM channel. And all it does is basically taking these different frames, which were coming over the air, concatenating them and passing them up to the layer 3. And layer 3 is what basically makes a phone. So all the things you would expect a phone to do. There is a radio resource management sublayer, which is responsible for dealing with the radio channel. There's a mobility management sublayer, which holds, for instance, information about the network and the network name and so on, and a connection management sublayer, which provides the actual phone functionalities. So CM, or connection management, is further distinct in 3 other sublayers. CC for call control. So if you pick up your phone and do a call via 2G, this is the message which will be traversed and go to the sublayer we're getting at. Then there's SMS, the short messaging service sublayer, and the SS, the supplementary services. And the supplementary services help the other tasks or help the other sublayers to implement additional functionality. For instance, one can set up call forwarding via the supplementary services.
Okay, so now we know a bit about the GSM protocols stack itself. Let's talk a bit about GSM layer 2, as that will be also our target. So we start with a single LabDM frame. Now the single LabDM frame consists of the following struct. It contains 3 header fields, which is the address field, the control field, and the length field. And then there is the information field. The information field is typically, from an attacker's perspective, the most interesting part, because this contains the most information. The problem is that the information field in a single LabDM frame is very limited in size. So one of the main functionality of the LabDM layer is to be able to concatenate all these individual LabDM frames. To do this, you have to supply the right encoding in the length frame, because this contains a bit that will let the baseband know that it should concatenate all these frames. So the RR task is the first task that will actually receive this concatenated LabDM frame. The RR task will then look at the protocol discriminator. The protocol discriminator is the first byte of the information field. And from the example here, you can see that if the protocol discriminator is unequal to 6, it will forward it to the MM task. If it's equal to 6, the RR task will actually already parse the message itself. Now the MM task has sort of the same job as the RR task. It will again look at this protocol discriminator, and based on this value, it will either forward it to the CC task. So if the protocol discriminator is equal to 3, if it's equal to hex B, it will forward it to the SS task. And if it's equal to 9, it will forward it to the SMS task. And finally, if it's equal to 5, the message will actually stay in the MM task, and the MM task itself will actually parse the message. So the parts depicted in red are the layer 2 functionality, and the part depicted in green is the layer 3 functionality.
Now, having looked a little bit at Baseband itself, the cellular stack, and GSM layer 2 and 3, let's talk about our approach to fuzzing.
So there are many approaches to actually fuzz. The first one would be to fuzz a single function. So these are called single function fuzzers. And for example, in a baseband, this would be the ASN decoding. So these fuzzers will only fuzz the ASN decoding. A bit more advanced fuzzer will actually fuzz the whole task itself. So in this case, it will be the CC task, and if the CC task were to implement the ASN decoding, the fuzzer will reach the ASN decoding, but the fuzzer will also reach the other functionality of the task. And we can do this for the CC task, but we can also do this for other layer 3 tasks. Our approach, however, we want to fuzz the layer 2 task. And with the scheme that we've shown before, we think that it should be possible to let the baseband forward our message. So the idea here is that we fuzz the lab-the-m task, and then with this logic of the protocol discriminator, the baseband will forward the message for us to, for example, the RR task, the MM task, but also the tasks that were further down in the protocol stack, such as the CC and the SMS task.
For fuzzing itself, we decided to use the firmware framework, which is a full system baseband emulation framework. It's open source and was released in 2022. And what it allows us to do is to take the cellular modem firmware, which usually runs on the phone and implements a cellular stack, takes this out of the phone and put it inside an analysis host. And this analysis host can then run the firmware, obviously not with the physical parts of the cellular stack, because there's no notion of this in the emulation, but the layers above can be emulated with a full system emulation approach. Firmware allows us to inject packets to the different tasks, so the different sublayers of the cellular stack, and allows the task to process our inputs which we provide to the emulated cellular stack. Additionally, firmware allows us to extend the baseband firmware by adding and injecting our own tasks into the cellular stack, so we can actually dispatch and change the functionality of the baseband as we want to. Using this approach of full system emulation provides us different advantages which are crucial for our approach. First of all, firmware gives us out-of-the-box analyzable log messages, so especially in contrast to over-the-air fuzzing, we can easily see what's going on. It also provides coverage tracking and has indeed an AFL++ integration, so we can easily set up a fuzzer without additional engineering. And most importantly, as we attempt to fuzz the full cellular stack by injecting from layer 2, firmware and full system emulation, as it emulates everything, provides already the task interaction. So by default, if a message kicks in or results into forwarding of messages to yet other tasks in the stack, this is already supported and will be emulated as well.
So a fuzzing task itself in firmware is written in C. There is an AFL wrapper present to deal with the fuzzing itself. But the thing here is that the fuzzing task itself actually appears as an ordinary task according to the baseband, because the task itself is injected into the real-time operating system. And the nice part about this is that you can also use the baseband functionality. So a fuzzing task itself will consist of two steps, an initialization step and a fuzzing step. And the initialization step is necessary because some tasks require a state that is more stateful than the right after boot state that we get from firmware. So if we look at the example of the fuzz single setup, we see two functions, a pal mem alloc and a pal message send to, and these are actually functions from the baseband. So the pal mem alloc is just an allocation function from the baseband, and the pal message send to is a function to that you give your fuzzing input or your input itself, and it will actually put your data into the queue of the task that you're targeting. So we need to allocate an item start, we need to set some magic bytes, and then send it to the task that we're interested in to initialize the task. So we also have the fuzzing itself. So the fuzzed input, we get that from AFL. And it's really similar to the initialization step, but now we actually have a mem copy of our fuzzed input into the item struct. And then we again use this pal message send to send our fuzzed input to the task that we're interested in.
So which firmwares did we actually target with our initial fuzzing campaigns? We looked at Exynos-based firmware because these are supported by the firmware framework, and we looked at two firmwares in the very beginning for our fuzzing campaigns. First of all, we selected a firmware from the Motorola One Vision, which is the latest firmware that is available for this particular phone. The phone was released in 2019, the firmware is from 2022, and we choose this target because we already did some reverse engineering with it. We worked with it before, so we are quite familiar with how it looks like. And also the Motorola One Vision is a phone which is easily available for not a lot of money, so a good target to start your research with. Then we also looked into the Galaxy S10e with a firmware from March 2023, so the latest which was available at the time of our research. And we decided to look at this firmware because it's the latest, like the phone is the latest model supported by firmware. There has been some changes in cellular stack implementation so that firmware would not emulate more recent phones. That's why we use this, but also as it's a firmware version which is released after the firmware work was published, all the bugs which were found by that work are already patched in the firmware, so we were hopeful that we would only find new findings. Okay, this is more or less the fuzzing setup, firmware, fuzzing tasks, and certain firmware images. What were the challenges we had to overcome to actually make our fuzzing working? In a nutshell, there were 3 challenges. First, we needed to create the fuzzing task, so we needed to make layer 2 fuzzing actually happen. Then we needed to deal with a complex baseband state. Basebands are highly stateful, and we needed to get the state right, which is equivalent to overcoming fuzzing roadblocks. And lastly, we just saw that the firmware images we targeted were from somewhat outdated phones, maybe not the most recent firmwares. So we actually needed to look into how we can make sure that our findings, if there were any, would apply to modern phones as well. So let's start looking into challenge number 1, creating the fuzzing task. As said before, our goal is to start fuzzing from the LabDM task, so layer 2, and having our fuzzing input traversing the full cellular stack upwards from there. And for doing so, we need to initialize all tasks on the way. And this involves reverse engineering, because we need to find magic constants, like here's a header operation 2, or the message group, to make sure that the tasks we want to initialize actually do process the initialization message and are ready to receive further input. Here's the code for doing this for the RR task, but of course we also had to do it for the MM task, the CC task, the S task, and the SMS task. And in each of these cases, these constants were different, and it was basically spending some time reverse engineering the baseband firmware. So then we thought, hey, all our tasks are initialized. Let's start fuzzing. Let's try and see what happens. Unfortunately, the fuzzing was not successful yet. And let's have a look in what actually happened by taking one of the test cases we found and replay them and looking at the logs. So here's again our fuzzing plan. We want to fuzz layer 2, go through the stack, and we inject our fuzzing input to the LabDM, to the layer 2 task, and we can see some processing is happening. Also, especially noteworthy, there is some notion of add concat buff. So the frame concatenation is working as expected. Our fuzzing inputs is concatenated and processed by the glabd task and is forwarded up. We have the PAL message send to call, which is the baseband way to send messages to the RR task. The RR task takes its inputs, processes this as well, and forwards it up to the MM task. Now, with the MM task, we see something unfortunate. We see a trap message with 3 exclamation marks afterwards, so something is going wrong here. And the trap message tells us there's an invalid request for this state in MM decode RR data indicator message. So we initialized all tasks, but we are not able to proceed with the fuzzing yet, which brings us to challenge number 2.
Okay, so what do we actually mean with state? State can be seen as general fuzzing roadblocks. This is also the state of our presentation title. And the first step will be, how would you identify this state, right? So in this example, it's pretty straightforward because we have our log message. So the log message say that apparently the MM task is in the wrong state. So on the slides, you will see a Ghidra decompilation, and we know where this trap message is printed, so we can use Ghidra to backtrace, and then we see this decompiled output. So on the slides, we see that the baseband starts with a MM-getState call. And based on this value, there is a switch, and if the value is not correct, the baseband will print this trap message. So the MM-getState call is actually a fairly simple function because it only dereferences a certain memory address. So note, this memory address is, in this example, specific to the Galaxy S10e, but so this will differ per firmware image that you're analyzing. So at this point, we now know what we need to do, right? We need to make sure that the MM-getState call actually returns the right value. And we know what value it will read from memory. So the ID is known at this point. So on the left, we have the state variable memory address again. And as our fuzzing task is injected into the real-time operating system, we can just use simple C dereferencing. So on the left, we have the memory address, and on the right, we just dereference that memory address and supply the right value that will make sure that the switch statement will not print this trap message. So in this case, it is fairly simple, right? Because we have this log message. In some cases, we don't have the log message, but the idea is fairly similar. We reverse until we get it working. So these are very simple constants, right? But we also need some more advanced state. And an example of that would be a struct. In this case, on the left, there is an RR serving cell struct, and this typically contains information about the network. And you don't get this when the state is only right after boot, right? You have to really supply this to the basement itself. So there are some unknown fields in the struct, and the crucial thing here is that you only want to restore the very crucial state. Because the challenging thing about adding state is that you might over-engineer this part and then create some kind of conflicting state or state that you won't be able to recreate in a real-life setting. So the key idea here is that you only want to restore the very, very crucial state. So again, we start our fuzzing run. We again start with fuzzing the labdm task. It will again do the concatenation and forward it to the RR task. The RR task will again forward it to the task. And now we actually see a difference, right? On the bottom, in the previous slide, we had this trap message, and now we actually see that the task will forward our message to the CC task. So with adding state, we now made sure that the basement at least thinks it is in the right state to forward the message. And in this case, it forwards it to the CC because we specified the protocol discriminator to be free. And then finally, we see in the CC task itself, the CC task actually receives the message and does some things with the message and parses the message.
So this is very cool. We saw now that our messages would traverse the baseband stack as we wanted. The tasks are initialized, the state is initialized. So we should be able to start fuzzing again. And indeed, that's what we did. And this time we had success. Here is a screenshot of AFL++ doing AFL++ing. And what's impressive here is that already after just 1.5 hours of fuzzing, we found, or AFL++ found 15 crashes it deemed interesting. This is especially awesome in our opinion because the fuzzing speed itself is rather slow due to constraints of our approach. Now, if we take one of the crashes which were found by AFL++ and replay them in the firmware framework, we see some output, some log messages like this. So in this example, there was a message which went all the way to the task, prints a little bit about a short network name, does a little bit of different things, and at the very bottom, it will say, fatal error, PAL memguard corruption. This is an indication that some sort of heap metadata was corrupted, so we very likely, with this particular crashing input, triggered a heap-based buffer overflow or some other type of memory corruptions. So exactly what we were looking for. But now we have a problem, right? We found this in our emulation, but our emulation targets outdated firmware. So how can we replay it, or how can we make sure that these crashes would affect recent phones, or if the vulnerability is still present? And our idea was quite straightforward and simple. We decided, let's just take all the crashing inputs we found and try to replay them over the air to newer devices and see what happens. For doing so, we built a little bit of automation. So we took all the crashes, had some shell scripts which would automatically replay the different crashes and see what happens. And we used some open source tooling to create our own fake base station to send it out to the phone. This is our over-the-air confirmation setup. As hardware, we have a Faraday cage, so very important. Please adhere to your local legislation if you do this kind of testing. We used a Blade F20 as software-defined radio, which was commanded via Raspberry Pi 4. As software, as we are looking into the 2G stack, we used Yate and Yate BTS as base station and network and PC software, and we tested a variety of different phones. First of all, we decided to test against the Motorola One Vision and the Samsung Galaxy S10e. So the same phones we had in our emulation. This is just to confirm that the crashes we found are actually real true positives and not based on emulation inaccuracies. If this was to succeed, we will then replay the crashes also against newer devices, Google Pixel 6 and the Pixel 8 phone, or Samsung Galaxy S22 and A14. And when we replayed those crashes, we will see an ADP log cut, so in the logging infrastructure of Android, some output looking like this, a lot of repeating messages, but just zooming in on one of those, it will say modem crash, modem is state crash exit or state crash reset. We would also see the connection bar on the phone going to disappear. So these are very good indications that the bugs we found in emulations are actually present on the real phone, also of more recent devices, which is pretty awesome. So let's have a look at what kind of vulnerabilities we found over our fuzzing campaign.
So with our approach, we were able to confirm the shown vulnerabilities. We have found 3 which were previously unknown and 2 which were internally duplicates. And we can see that these target different layers in the protocol, right? For example, the task, the task, and it also targets different phones. And this is the part where we show the proprietary side of the phones, right? We don't see the crashes or the vulnerabilities on each phone that we test. We can also see that the root cause itself can be different, right? It can be a heap-based buffer overflow, it can be a null pointer dereference, or it can be a stack-based buffer overflow, for example. Finally, we do want to stress that at this point, these bugs have been fixed. So let's look at an example. This is based on our emulation results. The phone does behave a bit differently over the air, but it happens when you send a malformed information message. So an information message is typically used by the network to supply the phone with information about the network. And these messages, or layer-3 messages in general, consist of information elements, or IEs. Each IE is either present, or is either mandatory, so the M, or is either optional. And it has a magic value that indicates whether it's present or not. So on the left, we have an example payload, and we see that the example payload starts with the value hex 5. And hex 5 is the protocol discriminator of a message. The next value is the value hex 32. And this is the message type of an information message. So there are lots of messages in general, but the information message is encoded with the message type hex 32. The next value is hex 45, and this is the short network name information element. So as you can see in the table, we've actually skipped the full network name. And this is totally fine because the full network name is optional, so we don't have to encode it in the message itself. And the last information element is encoded with the value hex 48, which is in this case the LSA identity information element. Okay, so what can be wrong about this is that we haven't talked about how the length of the actual information element is encoded. So in this example, we have the value hex 48 for the LSA identity information element. And for this specific information element, the length of the information element is encoded in the bytes after it, which is in this case the value hex 41. Okay, so how can this be a problem? For that, we look at the code itself. And we first see that the baseband tries to retrieve the information element length. This will return the value hex 41 from our original payload, but we see that there is some sort of check. It checks whether the value is greater than 3, and if it's greater than 3, it will cap the value at 3. So apparently, this information element should be fixed to 3, and this is also what you see when you look through the protocol itself. This value should be fixed at 3. So at this point, everything looks fine, right? There is a mem copy, but the information element is capped at 3 bytes, so this should be fine, right? So now there is a lot of code, which is not particularly interesting for this talk. But at the end, there is another mem copy. And with the other mem copy, this UVAR1, or the 3 bytes, is not propagated. And instead, the IE length is actually used. And this is the hex 41 bytes of our payload. So it should have used the 3 bytes, but instead it's using the hex 41 bytes. And in this case, buff is allocated on the heap. And buff, or the baseband only thinks that the allocation size for the LSA identity information element should be 3, but instead we supply 41 bytes. It will do a mem copy with 41 bytes, and since buff is allocated on the heap, it will overflow the heap buffer, and this will then result in a heap buffer overflow.
So with all of this in mind, let's look at how this bug actually looks like in reality if we replay it over the air.
So in the demo, we will have two phones. On the left, you will see a Pixel 8, and on the right, you will see a Pixel 6. The Pixel 6 is the vulnerable phone, and we trigger the vulnerability by calling the vulnerable phone. So we do want to stress this is not strictly necessary, but it's just a convenient way for us to know that that Yate actually sent our payload, and we know whether it resulted in a crash or not. So here we can see that the phone will connect to the network. The network here is just a combination of the mobile country code and the mobile network code. And then on the right, we see a zoomed in image of the connection bars of the Pixel 6. So we start to call the Pixel 6. And we can actually see the connection bars disappearing, which was, in our case, a nice way of knowing whether we triggered the vulnerability or not. So let's reiterate a bit. We call the phone because we've specified Yate to inject our payload when we call a phone or when there are CC messages exchanged. So calling the phone will actually trigger the vulnerability.
Now, one nice part about this bug is that we also send the short network name as discussed before. So let's have a little look at what happens now if the phone wants to reconnect to the very same network, right? We just made it unavailable and crashed it. And now if we search for a network, it will tell us, hi, Black Hat US 24. So we crashed the phone over the air, and we supplied a malicious or a controlled network name as part of our demo. Now, let's look at the defenses. So what are vendors doing to mitigate and make those kind of bugs we found harder to exploit? And first of all, we really want to highlight that there has been a recent shift in vendors' approaches, and we see really more and more hardening in cellular basebands, which is awesome in our opinion. Just to give some examples, we see a lot of differently more used or recently introduced or more used defenses. For instance, in the Pixel 8 phone, we saw a heap sanitizer, which provides additional hardening to vulnerabilities on the heap. So exploiting heap buffer overflows becomes a lot harder. We also saw more consistent use of stack cookies or the execute never bit, so data execution prevention for ARM, so that in the end, there's not everywhere writable and executable code regions inside the baseband processor. Also, since Android 12, I believe, there is a allow 2G button, as shown here. And the allow 2G button allows you to disallow using 2G. So in the case of the vulnerabilities we discussed in this talk, they would be mitigated by disallowing connection to 2G, as the phone would never connect even to a rogue 2G base station in the first place. So let's wrap up this talk and come to the end. And first, let's talk a little bit about the limitations and future work.
So as we saw, the state itself is based on memory addresses, and these memory addresses will differ per firmware image. And it already takes a lot of time to do this for one firmware image, let alone if you want to analyze multiple firmware images. So there is definitely a potential to automate this process.
Then there's one question which keeps coming to our mind. What if we cannot replicate a vulnerability we found in the emulation over the air? Do we really know that this vulnerability is not present or fixed on a phone? Not really, because phones do behave differently, especially if the firmware is different. So to really make sure or have really deep introspection, we would probably need a firmware version which supports more recent firmware for more recent phones, so we can have an in-depth analysis and observability logs of what's happening for a given crashing inputs for a given firmware.
And finally, within this talk, we talked about the 2G protocol, but what about the 3G, 4G, and 5G protocol? But to do this, it would require more reversing, more harnessing, more adding states. So basically, you need to do more everything. But it also includes more interesting functions, more obscure functions, more parsers. So it's definitely an interesting topic to look at.
So lastly, let's talk a little bit about key takeaways. And for this, let's just recap again what we did. We fuzz tested layer 2, or had fuzzing input, which we're targeting, layer 2, and we found a lot of vulnerabilities in layer 3. And the reason we got there is we provided the necessary state to get there. So in our opinion, state is key to overcome fuzzing roadblocks, especially when fuzzing across communication stacks.
And additionally, even though we fuzzed relatively old firmware images, we can still see that these bugs that were present in those firmware images actually transfer to the newest devices.
And lastly, we want to really stress that despite years of research, despite a lot of people already looking at 2G, running fuzzers, doing reverse engineering, there are still critical and high impact vulnerabilities hiding in these legacy cellular stacks. So where possible, we would really recommend to phase out 2G and disable the use of the stack within the baseband. And that concludes our talk. We are happy to take questions here on the floor or later via email, or alternatively in the rep room, which will be Mandalay Bay B. Thank you.
Thank you.